All right, we're here for AP Physics, Universal Gravitation, Problem 8. Problem 8 says that the maximum distance from the Earth to the Sun, so that's our aphelion, right, closest point, our far point, right, aphelion away, right, farthest point away, is 1.521 times 10 to the 11 meters, and the distance of the closest approach, so at perihelion proximity, that's more closest perihelion, is 1.471 times 10 to the 11 meters. They tell us our speed at perihelion is 30.27 kilometers per second, and they want to know Earth's orbital speed at aphelion, and we're at the far point. But with their orbital speed, that's the first part. And then they want us to go ahead and measure some energies and then ask about the total energy. So, what I want to do is go ahead and find our speed at aphelion. So basically the idea is as we're going around, right, so I don't know, so here's the sun at the near point, here's perihelion, right, and then out here, we're at the farthest distance out from the sun, that's aphelion. And they're telling us, let's see, we've got, so like here, like maybe this is the speed at perihelion. What am I just saying? This is the distance out at aphelion, and this is the speed at perihelion, and this is the speed at perihelion. And then out here, we'll be going a lot slower. So here's the V at aphelion, but we'll have a much bigger distance out from the axis of rotation there. This is my R at aphelion. All right, so there we go. And so what we're going to do here is we're going to use conservation of angular momentum is the best way of doing this one. Just given this information. So the idea is, just a quick refresher, you say, hey, conservation of angular momentum. We remember that if I want, the big formula for angular momentum is the sum of the torque to time is the change in angular momentum. Right? So to change the angular momentum requires a torque, a twisting force through a duration, through time, an angular impulse, if you will. And we say, now in this case, the only force acting on the Earth as it goes around is gravity, the gravitational force from the sun, the only significant force. We're ignoring forces from like the moon and Jupiter and other bodies. We're just looking at force of gravity from the sun. And so you say, well, that's not going to exert any torque because it's acting right along the R vector always. It doesn't twist. So you say it's the force will be the torque is R cross F, right? And the R vector for, so say I look at some random spot here, the R vector is going to be going right along the way the force is going against each other. And when I do a cross product, I'm going to take the sine of the angle between, well, the sine of 180 is 0. So there's no torque. And so that means that delta L is 0, and that means that my angular momentum at any point in the orbit is always the same value. So I could say my angular momentum here at perihelion has to be the same as my angular momentum at aphelion. And so I can say, well, how do I calculate angular momentum? The way we do that for this case, we're going to treat the Earth like, at this scale, the Earth is like a speck going around the sun, right? It's a point particle. So we're going to say that L at perihelion, right? We're going to use L as R cross P. That's the formula we use for point particles when we want angular momentum for point particles. So here at perihelion, that'll be R cross P. Can I substitute an MV for P? Thanks. R cross MV, and this is at perihelion. And that's got to be equal to my R cross MV at aphelion. Now, the mass of the Earth is not going to be changing, right? And you can see that's going to drop right out here, isn't it? All right? Well, I'll drop it on the next step. Now, the cross products mean I need to take into account the sine of the angle between the velocity here, because that's the way the momentum's going. This is R cross P. Between the angle between R and P. P is just the way V is going, the way velocity is going, the way the momentum's going. So in this case, look, because I'm looking at these special points in the orbit, if I was here, that angle between the R vector going out like this, and the momentum vector going that way would be some weird angle. But here at these particular special points, at these 2 points in an elliptical orbit only, perihelion and aphelion, that's a 90-degree. So that's really handy. That cross product is going to give us a sine of 90 for both of those points. And sine of 90 is just 1. So that's going to drop out nicely. I can see now the mass of the object is going to drop out. So I'm left with just radius at perihelion, velocity at perihelion, right, is going to be equal to my radius at aphelion, velocity at aphelion. Okay? And again, they've told us both radii, and they told us the velocity at perihelion. So we've got these two values trying to find the velocity at aphelion. Let's just move that RA over here, and then we can plug in our values and solve, and life will be good. So when I do that, move that RA over here, I'm going to have RP over RA, and VP will be VA. And you can find that speed when it's at the far point. All right. I went ahead, I plugged in my values with my calculator already. And did all those calculations. Anyway, when I went ahead and did that, this comes out to be, am I really going to jam it in the bottom of the board? Yeah, I am. So I got 1.471 times 10 to the 11th over 1.521 times 10 to the 11th times the velocity, 30,270 meters per second. I converted from kilometers per second to meters per second. And when I did the math, I got a velocity of 29,275 meters per second for my velocity at aphelion. Okay, so that was part A of this extremely long to calculate out problem. It's not that bad. It's kind of annoying. Part B. I'm gonna be honest with you. I didn't really enjoy working this problem. A lot of AP Phys problems I enjoy working out and figuring out. I'm like, oh, no, doom, 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 doom. And I figure it out, and it makes me feel good inside. This one felt kind of like a slog. Anyway, part B. I probably shouldn't say that. But anyway, part B, it's because of part B. This is the part that was really annoying. A was fine. B says, hey, can you calculate the kinetic and potential energies at perihelion? And then part C, find them at aphelion. And then D, see if energy is constant. So I'm doing all these calculations with these numbers. So I want to find the kinetic energy here at perihelion. And so I'm just going to say, it's just going to be 1/2 mass times the speed of perihelion squared, right? Kinetic energy 1/2 mv squared. I'm not worrying about rotational energy, the spin of the Earth. It's going to be minimal compared to the translational. So I'm not going to worry about that. But if I do this, you say, it's just going to be 1/2. And then the mass of the Earth, at the top of the page, it tells you mass of the Earth to use 5.98 times 10 to the 24. Yeah, I think that might be a more recent. No. I don't know. I seem to remember that value being 5.972. I should probably double check and Google what's a better value. So I remember from time to time people do measurements and get better, more accurate measurements. We should double check that. Anyway, I'm going to use this value. Use this value for the problem. What's on the page? Velocity at perihelion. We were given that was 30,270 meters per second squared. So I can calculate that out, and I got 2.7397 times 10 to the 33rd joules of energy. All right. Now they want the gravitational potential energy at perihelion, and so I know that's going to be negative g mass of the sun, mass of the Earth over that distance there at perihelion. So that'll be a minus 6.67 times 10 to the negative 11. That's the universal constant. The mass of the sun is 1.991 times 10 to the 30th kilograms. That's at the top of the page. They do that value. And then the mass of the Earth, again, we're going to use that 5.98 times 10 to 24 kilograms. The distance to perihelion, they told us before, 1.471 times 10 to the 11 meters. When I punched that in my calculator, I got a value of negative 5.3, and I went down some digits, 5.3986 times 10 to the 33rd joules. I kind of knew that they were going to ask me to do more calculations with this number later, so I carried some extra digits to be on the safe side. All right, I mean, I really should round that off because the values I'm putting in only have 3 sig figs there, but you get it. Okay, next. They would like to know, now that was at perihelion, now let's calculate those values at aphelion. And so, it's the same formula, 1/2 mv squared. But now, of course, using the velocity at aphelion, okay, which is what we calculated in this previous part. So punching through 1/2 the mass of the Earth, 5.9 times 10 to the 24, 29,275. My answer from the previous part squared. And when I punched that in my calculator, I got 25625. Oops. Times 10 to the 33rd joules. Okay. And then do the potential energy at aphelion, UG, gravitational potential energy at aphelion. And it has to be minus G, mass of the sun, mass of the Earth, over that distance out at aphelion. When I go ahead and do that calculation, 6.67 times 10 to the negative 11 is the capital Z, big G. The mass of the sun, 1.991 times 10 to the 30. And mass of the Earth, again, so it's just like the top line there, 5.98 times 10 to the 24. Okay, now I'm going to divide by the distance at aphelion. They told us that that value was 1.521 times 10 to the 11 meters. Okay, and I punched that in my calculator, and what I came up with was, right, negative 5.2212 times 10 to the 33rd. It's 33rd joules. Shoo! Okay, that was parts B and part C. Now part D, they ask, is energy conserved? And I know that for the Earth going around the sun like this, the Earth-Sun system, we're saying there's really just the two types of mechanical energy we're measuring here, and that's that kinetic energy and gravitational potential energy. So I'm just going to say the total energy is gravitational and potential and gravitation, kinetic energy and gravitational potential energy. And so I'm just going to add these together to get the total energy at perihelion, and then add these two together to get the total energy at aphelion, and compare the two. What can I say? When you go ahead and you add those up, right? This and this. At perihelion, I got negative 2.6589. 2.6589. Yeah? Yes. Times 10 to the 33rd joules. And then when I took these two values and I added them up, I got that total energy was negative 2.6587 times 10 to the 33rd joules for the total energy. And you see, first of all, you're like, wait a minute, I'm getting a negative value. Is something wrong? You say, no, no, no. Remember, the total energy has to be less than 0 if you're bound in an orbit, right? If you had a positive amount of energy, you'd have enough to get out to infinity. You wouldn't be bound. You could escape out to infinity where potential energy is 0. You get a positive amount of energy. So no. So definitely we need a negative answer for our total energy. When I compare these numbers, you say, gosh, those two numbers are really, really close. They're only off when you get to the 1, 2, 3, 4th decimal point there. And you say, remember that I should have rounded these, right? Because we're putting in sig figs, only 3 sig figs here for the mass. So you're like, yeah, those are the same. Okay, within the accuracy of our values here, those are the same. So energy is conserved. And you say, well, of course energy is conserved. There's no significant outside force involved in our calculation here to do work on them. So the energies have to add to be the same. So this is another way of analyzing orbits. In the previous part, we used like angular momentum. If we wanted to, if we really, really wanted to, we probably could have done like energy calculations, right? Perhaps. And done like 1/2 mv squared and 1/2 mv squared of potential energy, negative g m over r squared. But it really is quicker and easier to do angular momentum conversation. I mean, look at that. RV is RV. I mean, come on. It's hard to get much easier than that. All right. So yeah, you want to use angular momentum conservation if you can. Okay. Yep. That's this problem. Problem 8.